I request all the participants to please keep themselves muted during the entire session. Dr. Ratanpal specializes in the general theory of relativity and orbital dynamics. With extensive experience in teaching subjects like MATLAB, Python, image processing, and differential equations, Dr. Ratanpal has made significant contributions to research, evidenced by his numerous publications in reputed journals. Today, he will be sharing his expertise on image processing and computer vision as part of a 2-week faculty development program on MATLAB for engineers and scientists, bridging theory and application. So with this very brief introduction, I would like to request you to please take over the session and enrich us with your presentation.
Yeah, thank you. Thank you, Surbi. Am I audible?
Yes, sir, you're audible.
Okay, okay. So, first of all, I would like to thank Dr. Maharaja sir and the MTTF for inviting me for this session. Well, today I will be talking about the image processing. I will be talking about. Hello. Yeah, so today I will be talking about the image processing. So, is my screen visible first of all?
Yes, sir, visual.
Yeah, yes, so it's visible. Okay, so basically, whatever the object we see, the light is incident to the object, it is reflected back, and our eyes, reflected back to our eyes, and our eye can see it. So, before going for color image processing, I would like to talk about the gray level images. So these gray level images are the monochrome images, that is a two-dimension function of the intensity, of the light intensity, where x and y are not the usual Cartesian coordinates, but they are referred as the spatial coordinate. So this intensity function can be bifurcated into two parts. The first one is illumination and second is reflector. The value of illumination lies between 0 to infinity and reflection is 0 to 1. So if the value of reflection is 0, then it's a totally black, and if it is 1, then total reflection, that is white. So this images, can be this function fxy can be written as two-dimension array of color images. That is the pixel of the color images. That is the I'm sorry, uh, array of pixel. The pixel has the values between 0 to 255. Between 0 to 255. Now, why these values are between 0 to 255? Because pixel is stored in 1 byte, and 1 byte is equal to 8 bits. And bit can take the value either 0 or 1. So either all can be 0 or all can be 1. So if you convert this binary number 0008 time to the decimal, the number is 0. If you convert this 8-bit binary number 1111 and so on 8 times, then its corresponding decimal value is 255. So the corresponding decimal value is 255. So here first we see how to convert a colored image to the gray level image. So is this clear to all of is this visible to all of you? MATLAB code? Yes?
Yes, sir.
Okay. Okay. So, uh, for reading the yes, for reading the image, the function is imread, and um, there is an image called image.jpg in my folder, and I'm reading it. After that, to this value, this is the variable, and this variable contain the array of pixel values, and the size of A will determine the array size. Then I will show in figure 1 plot IM show A, that is the original image. And to convert into gray level, what I will do, colored image to gray level image, what I will write, RGB to gray A, and MN is equal to size of B. So it will be the image, gray level image, size of the gray level image, and I will show the gray level image B. So if I run this code, then you can see that the size of colored image is 1080 cross 1920 cross 3. That means it is a three-dimensional array. Three-dimensional array. And this is the colored image. This is the colored image that is in the image 1. And this is the gray level image. Up to this, is it clear to all of you? Yes or no?
Yes, sir.
Yeah. Okay. So now we will proceed further. We'll proceed further. We'll see what are the. I will cover. I will cover the theory portion also, because the title says theory and practical. Okay. So now, neighbors of pixel. Neighbors of a pixel. So we have, suppose we consider the 3 cross 3 image. That means only 9 pixel we consider. Here this middle coordinate I will call xy. This coordinate will be x minus 1y. This will be x plus 1y. And in the similar way, up will be xy plus 1 and down will be xy minus 1. Now these 4 pixels are called 4 neighbors of P. Are called 4 neighbors of P. Then I have this diagonal pixels also, whose values are x plus 1, y plus 1, x plus 1, y minus 1, and so on. So uh, these neighbors are called diagonal neighbors of P and diagonal neighbors of P. Now, a pixel P is said to be, uh, or the pixels are said to be in 8 neighbor if they are either in 4 neighbor or diagonal neighbor. So total there will be 8 neighbor, um, 8 neighbor pixel. Now connectivity between the pixel. So this connectivity is defined as 2 connectivity, 4 connectivity, and so on. So now what we mean by 4 connectivity? So you consider 2 pixel P and Q. We say that Q is 4 connected to Q if Q is in one of the 4 neighbors. And Q is said to be 8 connected if Q is in one of the 8 neighbors of P. One of the 8 neighbors of P. Now, connected components. For, what we need to do is, here to find scan the image, and the image, um, just a moment. This image is scanned from left to right and top to bottom. Images from left to right and top to bottom. Now, here we are talking about black and white image. Now, in the black and white image, what will happen? The pixel value will be either 0 or 255. For sake of simplicity, we treat 255 as 1. So, the pixel value P is either 0 or 1. Now, if the value of P is 0, the first pixel we scan from left to right and top to bottom. If the first value is 0, then we say we move to the next pixel horizontally. If the value of P is 1, we examine the top and left neighbor, top neighbor and left neighbor. If no label is assigned, then we assign the new label to P. And if both are 1, then we assign the same label, that of either of P and Q. So here are various situations. So you have 0. So 0 first pixel is 0. So 0, and so we simply move to the next pixel. Again, next pixel is 0. Is it okay? So now again it is 0, so we move to the next pixel. Now this pixel has the value 1. So what we do is we see the top pixel value and left pixel value. Since it is on the border of the image, so there is no left pixel value, and the top pixel value has not any label, so we assign the new label to it. Okay? Then, after assigning the label, we go to next pixel. 1, again the value is 1. We look at the top pixel, we look at the left pixel. Top pixel does not have the label assigned, and left pixel has the label 1. So we assign the same label 1 to it. There is another situation. Say scan the first pixel, its value is 1, so we assign the label 1 to it. Then again move to the next pixel, and we see the top pixel and left pixel. There is no top pixel, but there is left pixel which has the label 1. So same label we will assign. So here we move to the third position now. Now here we see top pixel and left pixel. So both has there is no left pixel, so we will assign the label 1. And similarly for the fourth one. Now here 0, so we simply move to the next pixel. Then this pixel has the value 1. So we look at the top pixel and left pixel. Left pixel does not have any label, so assign the label 1 to it. Now we will move to what the new pixel. Again we look at the top pixel and the left pixel. The top pixel does not have the value and left pixel does not exist. And we have already assigned 1, so we assign the 2, the new label 2. In a similar manner, if we have the 1 at the next level, then we see the top pixel and left pixel. Now the top pixel has the label 1 and left pixel has the label 2. So any one of them we can assign, but we assign with the minimum. To have the minimum labels, what we will do is we will assign the minimal of 1 and 2, so which is 1. Then 0, move to the next position, 0, move to the next position, 0, move to the next position, and here it is 1. Anyway, so this is the way of labeling is the way of labeling the connected component. Now, image processing is nothing new. I mean, digital image processing is nothing new concept. So what you have is whatever we have studied earlier that we have to implement in the context of image to the matrix. So colored image is what you can say 3x3 array is a, I mean, m cross n cross 3 array, and gray level image is m cross n array. So we have the relation. So definition of relation which we have studied, reflexive relation is said to be reflexive if A relates itself. It is said to be symmetric if A relates B, but B does not. That implies B relates A. And transitive, if A relates B, B relates C, then A relates C is said to be the transitive relation. So, in real life, we have many relations. So now, can you say the relation brother is symmetric? Yeah, please answer. Relation brother, is it symmetric? If A is a brother of B, then B is a brother of A. Is it symmetric?
Yes, sir.
No, it is not symmetric because B may be the sister of A. Got it?
Sir, pardon, please.
The relation brother is not symmetric because if A is the brother of B, then B may be the sister of A.
Yes, sir, but it depends what is A.
Huh? No, it
Sir,
depends not what is A, it depends what is B. It depends on what is B. A is the brother of B. So B may be a boy, B may be a girl. Okay?
yes, sir.
Yeah. Okay, so now transitive closure. Now transitive closure means what? We find the equivalence relation using, applying the matrix. So we consider the equivalence relation. Let us consider this relation. A relates A relates B, B relates D relates B, C relates E. So if an element is related, we write in the matrix as 1. If it does not relate it, we write it as 0. So this is represented by the matrix like A, B, C, D, E, A, B, C, D, E. A relates A, so 1. A relates B, just a moment. A relates A, so 1. A relates B, so 1. B relates D, so 1. D relates B, therefore 1. And C relates E, therefore here it is 1. And at rest of the places, it is 0. Got the idea? Got the idea? Representing the relation in terms of this thing. Yeah. Okay. Now, what we do is we define a transitive closure matrix of this matrix B by the relation if A relates B, B relates C, then A relates C. A relates B, B relates C, then A relates C. So, for example, A relates B, and you can see that uh, D relates B. D relates B is equivalent to say B relates D, because that's the equivalent relation, because it's the equivalence relation. And therefore, what you can say, A relates D. A relates D. So this transitive property, this matrix will give us, transitive closure will give me this matrix, and relation is written as R dash is equal to AA, AB, AD, BB, BD, and CE, and so on, and so on. Now, how to obtain this? We can calculate the transitive closure B plus by B plus B squared plus B cube plus and so on B raised to n, where n is the dimension of the matrix. So, here we will see the MATLAB program for transitive closure. So here I have defined my matrix A, and I will find the dimension of the matrix. N is equal to length of A. Earlier there are all zeros, and then I will say for I varying from 1 to n, sum is equal to sum squared, and then after that what we will do is, wherever the value of B is non-zero, we will replace that value by 1. And therefore, if I run this program by writing here trans closure, so you can see the transitive closure is 11011 01010, and so on. You can match. The answer is same. Is it okay? Hello? Is it okay? Shall I proceed further? Hello? Can you hear me? Okay, okay. Yeah, sure. Okay. So we proceed further. And in the same way, the distance between the pixels, this distance, metric, we have studied in the metric theory. So we have the pixel xy, pxy, qst, and zuv. Okay. So we define the metric as the metric should satisfy the distance between p and q should be greater than or equal to 0, greater than or equal to 0. Distance between P and Q is equal to 0 if and only if P is equal to Q. Distance between P and Q is equal to Q and P, and the triangular inequality must be satisfied. And the triangular inequality must be satisfied. In a similar manner, we can define the distance in terms of um, image by writing in terms of image by defining the Euclidean distance PQ, which is equal to x minus s squared plus y minus t squared is to 1 by 2. And that's a usual distance. That's a usual distance we are defining, the distance between 2 points. Okay. Then there is a D4 distance. It is also known as the city block. It is also known as city block. The pixel P has the coordinate xy. Q has the coordinate st. So D4P is x, absolute value of x minus s plus y minus t. So if I consider any pixel, so the middle one I'm considering, so its distance from itself is 0. These 4 diagonals will have 4 neighbors will have the value 1. By this definition, the diagonal neighbors has the value 2, 2, and distance from 0 to the rest of the coordinate system, this coordinates, accordingly it will become 3, 4, and so on. So you see, this is 0, 0, this is 0, 1, 0, 2, 0, 3, 0 minus 1, 0 minus 2, 0 minus 3. And this is 1, 0, 1, 2, I'm sorry, 1, 0, 2, 0, 3, 0, minus 1, 0, minus 2, 0, minus 3, 0. So using this coordinate system, particularly, I mean, if you want to calculate the distance of this pixel from this pixel, then this pixel has the coordinate 0, 0. This pixel has the coordinate what? Minus 2, 0. Put in this formula the value of x and y, s and t. So you will get the value 2. And d at distance is the maximum of x minus s and y minus t. So this value, the pixel value, suppose I consider the middle pixel, its distance from itself is 0. These are the pixels at the distance 1, and these are the pixels at distance 2. So there are various ways of defining the distances, and the arithmetic operators like addition, subtraction, multiplication, division, as well as logical operator and, or, and not are applied to it. Now this rotation, this actually in mechanics, we have studied the rotation of the body along x-axis, along y-axis, along z-axis. So in that, what we have is, we have a 3 cross 3 matrix. So the fourth row and fourth column is not there. Fourth row and fourth column is not there. So what you have is, about when you are talking about the x-axis, so you consider first two columns. You consider this first two rows and first two column, and cos theta, sin theta, minus sin theta, cos theta. At the rest of the places 0, 0, 1, 0, 0, 1. Z is 0, 0, 1. So now, I'm sorry, yeah, about z-axis, not x-axis, about z-axis. So Z is 0, 0, 1. About xy, about x-axis, so it will be 1, 0, 0, because the what you can say about this bases for the x-axis are 1, 0, 0, for y-axis 0, 1, 0, and z-axis 0, 0, 1. So we have here 0, 0, 1, 0, 0, 1. Here 1, 0, 0, and at the last we have 1, 0, 0. Okay, so here what you have is cos alpha, sin alpha, minus sin alpha, cos alpha. So this way we can rotate about the y-axis also. Rotate about the y-axis also. Now, the image rotation. The image rotation is, for example, I have an image in my folder. So I will write A is equal to IM read. So it will be, A will be the array, three-dimensional array. Okay, and this is this file name is image. Its type is JPG. B is equal to RGB to gray A, and I will rotate B at the angle of 30 degree, and I will show the image formed by this array, two-dimensional array C. So I will say rotate IM. Just a moment. Rotate IM. So this image is rotated at 30 degree. You can rotate it to say 60 degree. This number is in degree, not in radian. So it is rotated to 60 degree. You can rotate it to 90 degree. You can rotate it to 180 degree. Got the idea? Yes or no? Hello. Hello. Can you hear me? Yeah. So shall I proceed?
Sure, sir. You can proceed. Hello. Hello. Am I audible?
Hello. Am I audible?
Yes, sir. You are audible, sir.
Yeah. Okay. So now the image enhancement actually is done to process the image. The basic thing of the image enhancement is the histogram. Now, histogram we have studied in either our 11th or 10th or 11th standard. So what we have is now here how to plot the histogram. So here the pixel values are from 0 to 255. So we have to count how many pixels are there having value 0. So that much unit bar we form. How many values, how many pixels has the value say 10? So pixel value 10. So those number of pixel bar, we will plot it. And how many values has the value 255? So accordingly, we will plot it. So now this histogram, you can either stretch or contract, and accordingly the image will be displayed. Accordingly, the image will be displayed. So for the contrast intensification, the histogram is used. Histogram is used. So we in the image, if we have a noise, so we can remove the noise by using the histogram. Okay. So the contrast intensification. Actually, I'm telling you the process of contrast intensification. Um, Here, what we have is linear stretching. We stretch the histogram. So linear stretching is L is equal to L max minus L min divided by M max minus M min into M minus M min plus L min. Now, what is that? What is that? So suppose we have this much. This is the frequency table that pixel value 0. There are 0. Having value 0. There are 0 pixel, 1, 0 pixel, 2, 12 pixel, 3, 8 pixel, and so on, 7, 0 pixel. So what you have is we want to reduce it to, we want to, sorry, this is how this is formed. So this is formed from दिस इमेज, ये एक इमेज है, ओके। इस इमेज में से ये फ्रीक्वेंसी टेबल फॉर्म किया गया है. We have formed this frequency table from this image. You can see there is no 0 in this. There is no 1 in this image. And the number of pixels having value 2 are 12. So accordingly, we form it. So slope is Lmax minus Lmin divided by Mmax minus Mmin. Now, Lmax, what is Lmax? Maximum value. What is the maximum value in this pixel? So here, just a moment. Maximum value is 7. Why 0 to 7 we have considered? Because we are taking the 8 bits only. Therefore, we have taken from 0 to 7 only. And 7 minus minimum, that is 0, divided by M max. Now, M max is 6 here in this image. It is 6. And M min in the image is 2. So, it is 7 by 4. And we got this formula. So applying it for M is equal to 2, that is 2 will be shifted to 0, then 3 will be shifted to 2, 4 will be shifted to 3, 5 will be shifted to 5, 6 will be shifted to 7, and the linear stretching gives this one. This is the original image and matrix of the original image, and this is the matrix of the transformed image. Okay, is it clear?
Yes, sir, it is clear.
Yeah. So now let us see the MATLAB code for this one. Yeah, first, this is the, converting the image into gray level. So RGB to gray. And when we run this, we get this gray level images. Okay. Contrast intensification. So for contrast intensification, first of all, what we will do is we will read the image, then we convert it into gray level. Then there is IM adjust. IM adjust. IM adjust increase the contrast of image by mapping the values of the input intensity to new values such that 1% of data is structured at low and high intensities. So IM adjust. Second is histogram technique. Histogram technique. And the third is, so B hist is hist D. And then adaptive histogram technique. So now we converted, into the, the original, what you can say, original image into the gray level image, and gray level image is a matrix. Then using 3 techniques, we got 3 another matrix. So in the subplot, in the first one, I am showing the original. Second one, I am showing by image just, and third is using histogram technique, and fourth one using adaptive histogram technique. Just a moment. So this is the original image. This is using image adjust. This is using histogram. See the contrast intensification. ठीक है, contrast जो है वो remove किया है हमने. And this is adaptive histogram technique. So you got the idea? Yes or no? So shall I proceed? Type in chat box. Yes. Okay. Good. Okay. Now, sharpening the spatial filters. Sharpening the spatial filter. Now, before this, you should understand what we mean by, blur image, how to, remove the blurriness of the image. How to remove the blurriness of the image, and how to make it sharper, and how to make it sharper. Now, here what we have is any pixel. It's a window we select. Window means what? The pixel neighboring pixels we select. Say, for example, 4 neighboring pixel we select. So we make the average of those 4 pixels, and pixel average of those 4 neighboring pixel, and what we do is we that average we replace the original pixel value by the average value. So that image which we got using averaging, that will be what? The blurred image. That will be what? The blurred image. Applying the inverse technique, applying the inverse technique, we get from blurred image to the original image. And now, for sharpening the spatial filters, what we have is we have to define the derivative. Now, this derivative we have to define in the digital image, so whose values are discrete. So the derivative at flat segment must be 0. It should be non-zero at the slope, and it will should be non-zero at the along the ramp along the ramp. So second order derivative also must be flat, must be 0 in the flat area. That means at the top of the slope it is 0. Then it should be non-zero at the sides of the slope, and we define like this: fx is equal to fx plus 1 minus fx. You can define discrete, you in the discrete set of values, you can define the derivative. And similarly, the second order derivative. In the same way, we have the derivative filters. For example, gradient filter, that is del f by del x plus del f by del y. And this is gradient filter has the value gx squared plus gy squared is to 1 by 2, where gx is z9 minus z5 and z8 minus z6. So for this z1, we will consider, for this z1, we consider these 4 values, and z9 minus z5 and z8 minus z6. Then we have the Robert cross gradient filter, that is the square of these values raised to 1 by 2. And this is almost same as Euclidean distance, almost same as the Euclidean distance. And we have the Sobel operator, and we have the Sobel operator. Now we will see the algorithm for blur the image. So here I am reading the image.jpg, and stored in the variable called im. And then output image is blur that has two arguments. One is the digital image in form of matrix, comma, number of windows, say 2. So here, window of 2 pixel. Okay. Now it is calling a function blur. So I will move to the function blur. So function result is equal to blur imgw. And here first we will create a copy of image, because at last what we are doing, we are making changes in the copy of image, Okay, so this is the algorithm, that gradient algorithm, so that we perform from top to bottom and left to right, and the result. And here if I run it, so you can see it is taking a lot of time. It is taking a lot of time actually when you write some code, because the size of image is very large. Okay, I think it will take the 15 to 20 minutes. So I will not run this code, but let us say sharpening the image. So I'm reading the image, storing in the matrix called B. I am creating a sharpening. I'm creating another matrix which represents the sharpen image, and uh, the function to sharpen the image is im sharpen and B. See, actually, if you want to sharpen the image, you have to develop your own logic, which gradient filter you are applying. Otherwise, you may also use the inbuilt functions of the MATLAB. So the writing the code is this much difficult. And here, sharpen B, and you can see that if I run this code, so this is the original image, and this is the sharpen image. This is the original image, and this is the sharp image. Very little difference you can see, in the sense that this original image is already fine. It does not create any, what you can say, noises, etc. So you can see that. Is it okay?
Yes, sir.
Yeah, fine. Now, going further, so now the frequency domain filtering. So what we do in frequency domain filtering, um, frequency is directly related to rate of change. So we associate frequency in terms of Fourier transform. So the slowest frequency components will be UV is equal to 0, 0 in the gray level image. So what are the, what are the steps involved in it? The steps involved are, first you read the image. First you read the image. So it will be converted into the matrix form. That matrix, you multiply it by -1 raised to x plus y to center the transform. Then apply discrete Fourier transform to that modified or centered image. Okay, multiply this discrete Fourier transform matrix with a filter function h of uv. So what are the filter function that we can see over here? So there are low pass filter, high pass filter, okay, and so Butterworth low pass filter, Gaussian low pass filter, and so this is low pass filter. Now, what do you mean by low pass and high pass? Yes, can anybody say? Yes, can anybody say? In the pipe, the water flow is there. If I want that water flow should be less, so I will add the barrier in that, right? So the less water will be transformed. Less water will be the output, and that is the low pass filter. High pass means now I want to increase the water flow. Okay, so it is high pass. So in the image also it is the same thing. The passing of light. So if you have a torch, you keep a white cloth, okay, before that torch and see what is how much light is passing. Then you put different color clothes, say yellow color, green color, and see light is passing high from which one. So which one that color will represent that high pass filter, and from where the light is passing low is called the low pass filter. So now we apply filter function HV and compute the inverse discrete Fourier transform in the step 3. Obtain the real part of discrete Fourier transform in the step 4 and multiply the result by -1 raised to x plus y to get the image. -1 raised to x plus y to get the image. So what is the meaning? The meaning is you read the image, multiply it with -1 raised to x plus y to center the image, apply the discrete Fourier transform. If you want to blur the image, then apply the low pass filter, then apply the discrete Fourier transform, then obtain the real part, then multiply with -1 raised to x plus y. And if you want to sharpen the image, then apply the high pass filters. Then you apply the high pass filters. Is it okay? Yes or no? Now, removing noise is one of the things. So, in the image, if our images, no hard copy of the images are kept for a longer time, then what you can observe is there is a lot of noise in that, and that noise is kind of black dot and white dot, black dot and white dot. So those black dots black dots are called peepers. Okay, Kali Mirch, peepers. And white dots are called salt. Okay, so in the image, how to remove the pepper noise and salty noise. So first of all, I have the original image which I'm reading, and then I'm converting into the noisy image. The noisy image will contain the pepper and salt with what you can say the radius as 0.02, and then I will remove this noise by median filter. Median filter means what? We take the pixel, we take the four neighborhood, and then we find the median and replace the pixel value by the median. So in the first image, the first part, I'm plotting the original image. Second, noisy image, and third, noise removed. Okay, so if I run this in my folder, there's a picture called 8 Anna. Okay, and let me run this. So this is the original image. This is the original. Pepper and salt. Pepper and salt are mixed. And through the median filter, I'm I'm having the noisy removed image. What you can observe is this original image also contains some pepper and salt. You can see here, right? Which is removed to the certain extent because here there are salt. You can observe. Yes? Is it clear? So shall I proceed further? Yeah. So shall we proceed? Yeah. Okay. Now this is about the pepper and salt noise. Now color image processing basically consists of RGB model. RGB stands for um, red, green, and blue. Red, green, and blue. Actually, what we have is this RGB model is based on X, Y, and Z axis. So let me show you. That X, Y, and Z axis. So here you can see that these bases, origin is 000. The bases 100 represent rate. Then green 010 RG. Z-axis B, that is 001. Then intersection of red and blue is magenta. Intersection of green and red is yellow. Intersection of green and blue is cyan. And this color 111 is nothing but white. You got the idea? right?
Yes, sir.
Okay. Now, so blue plus red is magenta, blue plus green is equal to cyan, and red plus green is equal to yellow. Okay. So the color image represent the three-dimensional image. Okay. So that three dimension has R, C, and value 1, 2, 3. R stands for number of rows, C stands for number of columns, and 1, 2, and 3. That means on x-axis value, y-axis value, and z-axis value. So that is the red. Is x-axis is obtained by RC1. Green, y-axis is obtained by RC2. And z-axis, blue, is obtained by RC3. Now, there is another model. There is another model of color image processing, that is the HSI model, that is known as the HSI model. Hue, saturation, and intensity model. Hue, saturation, and intensity model. Now, RGB to RGB to HSI conversion. RGB to HSI conversion means red, green, blue to hue saturation model conversion. Okay. So if the hue is between 0 to 360 degree, hue is between 0 to 360 degree, then hue is written as theta if B is less than G. I'm sorry, there's no this image. There is no this bracket should not be there. This bracket, curly bracket, should not be there. It should be equal to theta if value of B is less than or equal to value of G, and is equal to 360 minus theta if value of B is greater than value of G. And theta is cos inverse. Now look at here. From RGB, we are converting to HSI, and first we are computing hue. So 2 times R minus G minus B divided by R minus twice R minus G square plus R minus B square plus G minus R minus G square plus R minus B, G minus B, and raised to 1 by 2. And raised to 1 by 2. That is theta. And the saturation is given by 1 minus 3 divided by red plus green plus blue into minimum value of red, green, and blue. And this is the intensity, 1/3 of R plus G plus B. And now converting from HSI model to RGB model. So if you want to convert from HSI to RGB model, then what we have to do is we have to see the different sectors. We have to see the different sectors. If H is between 0 to 120 degree, H is between 0 to 120 degree, then blue color is equal to intensity into 1 minus saturation. And red color is equal to intensity into 1 plus saturation into cos of hue divided by cos of 60 degree minus H. And green color is nothing but white minus green minus white minus green plus blue. Similarly, GP sector is 120 to 240. And in that R is equal to I into 1 minus H. Earlier there was B because there is a RG section. So first we compute B. Now it is GB section. So first we compute R. And G is given by this and B is given as 1 minus R plus G. And in a similar manner, we have BR sector between 120 and 360 degree, and this is the thing. Okay, now the subdivision of image is called the segmentation. Subdivision is called the segmentation. Now, how the segmentation is done? By recognizing discontinuity, by recognizing similarity, and region based and watershed based. So discontinuity means such as spot, line, or edges. Now, point detection. Sorry, so these are the, based on the direction and just a moment. This we define as per second order derivative, line detection, edge detection as per the second order derivative. But here, yeah, I have flipping the image from left to right and upside down. Flipping the image from left to right and upside down. So here, what I have is original image.jpg, which I am reading and storing in A. And this is the color image. So its dimension will be m cross n cross 3. Now, flip LR. Flip LR will flip the array elements from left to right. Flip the array elements or matrix elements from left to right. And flip UD will flip the array element from upside down. So I'm creating a subplot in which first portion I will show the original image. Second portion I will show the flip from left to right, and third image I will show flip from right to left. Is it okay? Right? So let me run this. Can you see the difference?
Yes, sir. We can see the difference.
Okay. So now just a moment. Let me check. PM image contrast, my flip, rotation, salt, pepper. Mm, black and white. Converting to black and white. Let me check. Just a moment. PM. Yeah, so let me copy this. Convert. Just a minute. No, just a moment. So the sub image I have run, then size of A I have commented. Sorry. So size of image is 1080, 1920, and 3. So what I want to show is A from 10 to 1000 and 20 to 2000. 10 to 1000 and 20 to 2000. Okay. And the third component I am neglecting. Show. So it will show the image like this. So it is showing the black and white image. Is it okay? It is showing the black and white image because third component is R, G, and B, and I'm not taking that. I'm not taking that. What I'm saying is from 10 to 10,000 values and the 20 to 2000 values only you take. Okay. So those are only displayed. Whether they are in red, they are in green, they are in blue, it doesn't matter. Okay, so it has taken. So this is the displaying the part of the image. I think this also will not work. Yeah. So this is about the this is about the image processing. This is about. Is the screen visible still? Hello. I don't know how to go back to this meeting. Yeah. Stop sharing. Hello.
Hello.
Yeah. So this is all about the image processing. So any doubt?
Thank you, sir. Thank you so much. If any participants have doubt, please raise your hand. I will unmute them and they can ask the question. Meanwhile, sir, I have a question.
Yeah.
Sir, like nowadays, so many softwares available for processing the image, like user-friendly processors like Photoshop and other softwares. So,
Yes.
what is the basic difference between image processing using MATLAB or any other software like Python, or the software that are used for image editing like Canva and Photoshop? What is the basic difference?
Yeah. So the basic difference I'm telling you. Nowadays, what we people are doing, we people are more interested towards the research, right?
Yes, yes,
Like image processing in different method. Say, for example, you have the various mask, various low pass filter, high pass filter. You create your own filter and see how much it is different from the other.
okay, okay,
Right?
okay.
So those will be implemented later on in those softwares, in those inbuilt softwares. Now the question is whether we should do the image processing or we should process the image like left to right, right to left, or
Yes,
convert from uh, color to gray, colored image to gray level image
yes,
using MATLAB or using Python, or we should use the any other software. Nowadays in mobile, the
yes,
Sketch
yes,
software is available.
yes, yes,
Sketch, that is also available, and various masks are available. So you see Snapchat, you have the
yes, yes, yes,
various lenses over there.
yes.
Is it okay? So now our question is that which one we should use? The answer is for what purpose we are doing.
Okay,
For what purpose we are doing. Okay. I
right.
have to share the image just to my friend, then I will use a different filter. Yes or no?
Yes, sir, definitely.
Yeah. And if I want to send it to some child, so I will use the filter of another, say, some animals or something like that.
Yes, yes,
So likewise, I mean, in the Snapchat, we do like that. So in a similar manner, for what purpose we are processing the image? Is it for just to see the, effect, or just using the different effect? We want to do it, then we will not waste our time in either MATLAB or in Python. Yes or no?
yes, sir,
Even we will
definitely.
not use the inbuilt function. even
Yes.
we will not use the inbuilt function. But you see, their codes are very typical. If you want to write code for image, I mean, you have to convert the original image from left to right, flip to left to right. So that is really typical. Okay. So,
Yes, sir.
uh, so that is really typical. So writing the code itself is the typical thing. So this is the research area nowadays we are doing. I mean, so that in good manner we can process the image. In a good manner we can process the image. You got the idea?
Yes, sir. Thank you so much. Thank
Yeah.
you so much for the answers, sir, and the full clarification. Meanwhile, if anyone wants to ask any kind of question to sir, please let me know. I will unmute them. On the behalf of the ICFA University and the Matter Thinking Foundation, thank you so much, sir. This was a very wonderful session. Hopefully, all participants have benefited with the concepts and
Just
clarification.
yeah, just a moment. Just a
Yes,
moment. I would like to get a sincere review from the participant.
yes, sir.
Please
Definitely, sir.
unmute. Please unmute all, and one by one they can raise your hand and give the so that I can improve myself.
Sir, actually, participants will get a feedback form as well. They will fill, and we can also share the review of your session with you after getting
Okay,
the feedback form, sir.
okay, that's good. But yeah, okay, that's also fine.
Okay. Thank you so
Yes,
much, sir. Hopefully, in future also, we will invite you as
yeah,
a speaker in your respective area. So, thank you so much for
yeah.
the session.
Thank you,
Thank you so much, and thank you all the participants for joining the session and attending the session. We will meet you tomorrow at the same time. As you know, tomorrow is the last session of this FDP. With the validity session, we will end this FDP. Thank you so much. Have a good
thank you,
day.
thank you.